Okay, so in my last lecture, uh, I have mentioned the last definition. Uh, what was that? The definition of a cyclic group, right? Cyclic group. That means a group G is said to be a cyclic group if there exists A belongs to G such that the cyclic subgroup generated by A coincides with G. That is, G is L angle right R angle A, where A is defined to be A is defined to be a generator of the cyclic group. For example, Z plus has two generators, say 1 and -1, right? One and -1. Okay. So can you, okay. So what about the case for the group Zn plus? Can you search out one generator for this group? Just do it now. Suppose, okay, in particular, let us have a look at Z6 plus. Okay. Okay. So can you search out one generator for Z6? Just do it now. One generator for Z6 plus. So the elements of Z6 are 0 class, 1 class, 2 class, 3 class, 4 class, and 5 class. Okay. So can you guess what would be the generator of this group if it exists? Does it have any generator of this group? Now natural guessing is that 1 class. Okay. So then 1 class plus 1 class, it is 2 class. 1 class plus 1 class plus 1 class, it is 3 class. 1 class plus 1 class plus 1 class, it is 4 class. And 1 class plus 1 class plus 1 class plus 1 class plus 1 class is 5 class. Now add one more. Then 6 class, right? But since the addition is modulo 6, so it must be equals to 0 class, as we know that 6 divides 6. So that is why, so it returns back to 0 class, this one. And again, if you add more 1 class, then you will find that you just getting these classes again. That is 1 class, 2 class, 3 class, 4 class, 5 class. So that means, so this shows that 1 class generates Z6 plus, right? That is Z6 plus is a cyclic group generated by 1 class. Okay. Now in the case of Z plus, we have seen that there are two generators. So in a cyclic group, there may be more than one generators can exist. But right. So this 1 class is a natural guessing for this group. Okay. But does there exist any other generator of this group except 1 class? Does it have any other generator? Can you guess? Any guessing from your end? You can write in the chat box. Any kind of guess that amongst these classes, except 1 class, does it have any other generator? Now, if you go to 2 class, suppose then 2 class plus 2 class is 4 class, and add more, it is your 6 class. That is 0 class. Then adding more, it will give again 2 class. And again, it is your 4 class. And again, if you add one more 2 class, then it will give you again 6 class, that is equal to 0 class. So it will, so this 2 class doesn't, so it is not a generator of this group, right? What about 3 class, 6 class? So it is 0 class. So again, if you add, then it gives you 3 class, add one more, again 6 class, it is 0 class. So again, it doesn't generate the group, right? Because it gives you only two elements, 0 class and 3 class. Now what about 4 class? So 4 plus plus 4 plus is 8 plus, that means it is 2 plus. Just one more, so it is 6 plus, it is 0 plus. Then adding one more 4 plus, then it will give you 4 plus again. Adding one more to that one, it will give you 2 plus. And then adding one more, it will give you again 0 plus. So it gives you 0, 2, and 4 plus. So it doesn't generate the group Z6. So it is not a generator. Now again we have the last one, that is 5 plus. So if you add 5 plus, then it gives you 10 plus. But what is 10 plus? Modulo 6, 4 plus. Add more. So it is 9 plus. Modulo 6, it is 3 plus. So it gives you 7 plus. So it modulo 6, it will give you 1 plus. Again, add one more. So it is 6 plus. That is 0 plus. Okay. And uh, okay. Uh, okay. Uh, so where is 2 plus 2 plus? Mm, mm, mm. I think I made a mistake. Yeah, it is 8 plus. Sorry, sorry, sorry. Yes, it is 2 plus, and then it is 7 plus, right? So it is 1 plus, and then you need to add one more 5 plus. Yes, yes, great. So it is 6 plus or it is 0 plus. Yes. So this 5 plus works for this group, right? So this implies 5 plus generates Z6 plus. So hence 1 plus and 5 plus are the generators of Z6 plus. Fine. Now if you look at these elements, these generators, you will find an interesting feature of these elements with respect to this 6. What is that? Note that 1 and 5 are the integers which are less than 6 and relatively prime to 6, right? Right. So this proves that, so this gives you an indication that can you generalize this feature to any Zn plus group for any n. So our intuition says that can you make it a statement that A class belongs to Zn will be a generator of Zn plus if and only if GCD of A comma n is 1, right? Now note that remark is that we have seen in the above example that that if we add a generator to 6 times up to 6 times, then it gives you the additive identity, right? Additive identity 0 plus. As 5 plus plus 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 5 plus. So it is actually 30 plus, so that is 0 plus. So that is, if we write down it as 6 5 plus, then it is 0 plus. And not only that, 6 is the least positive integer for 5 plus, such that this phenomena is happening, right? So 6 is the least positive integer for which 5 plus satisfies this property. So we need to generalize this concept to any group. That means, so we can define, let G be a group and A belongs to G, be any, suppose it is non-identity element. Okay. Okay. Be any non-identity element. Okay. Then 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 we can consider the elements which are a e a to the power 0, a1, a square, a cube, a4, a to the power n, and so on, right? And a to the power minus 1, a to the power minus 2, a to the power minus 3, this one, right? So you can consider these elements. Okay. Now in some moment, in some situation, if it happens that some a to the power r equals to a to the power s for some r comma s belongs to z. Okay. So suppose you are just doing the powers of a and considering these powers of a. If at some moment you find that two different powers gives you the same element, then what is going to be happening? Okay. Then so a to the power r equals to a to the power s means a to the power r dot a to the power minus s equals to a to the power s dot a to the power minus s. Suppose r is greater than s. Okay. R is greater than s. Okay. This implies a to the power r minus s equals to a to the power s minus s, that is a to the power 0, which is e. So that means this gives you that some power of a is going to be identity, where r minus s greater than 0. That is, you have found out some non-negative integer for which the power of a equals with identity, and this gives rise to apply well ordering principle. That means, so now we can set up a set P which is k belongs to z plus. That means set of all non-zero, set of all positive integers, and we are considering those k for which a to the power k is identity. Now this P is non-empty as r minus s belongs to P. Okay. Here we should write down that rs where r not equal to s. Yes. Okay. So this P is non-empty. So this implies P is a non-empty subset of Z plus, which which has which must have sorry which must have a least element k0 due to well ordering principle, right? Due to well ordering principle, that is, there exists a least positive integer k0 such that a to the power k0 equal to identity. Okay. Then this k0 is defined to be the order of a, is defined to be the order of k. Okay. order of k. So the condition was that you need to have one non uh, you need to have one positive integer for which a to the power k must be identity, and then it gives you one least positive integer k0 for which a to the power k0 is identity, and this k0 will be the order of the element, right? And for example, in this example, the above example of Z6, the order of 5 class is 6. Here, the order of 5 class is 6, right? Now, one may say that suppose you do not have any such positive integer, okay? Then we say that if no such positive integer exists, k exists for which a to the power k is identity, then we say that the element A is of order infinity. Okay, this just notation. Or one may say that the element A is of order 0. Okay, or one may say that the element A is of order 0. Now, in either case, we denote the order of an element A belongs to G as OA. Okay, so if it is a positive integer, then order of A is positive, and otherwise it is 0. Or if you consider the case where you are saying that the element is of order infinity, then order of A is infinity. That symbol. It means that there exists no positive integer k for which a to the power k is identity. Okay. Now do not dilute the cases. That means the order of a group and order of an element. Don't mess it up. The order of a group means that is the cardinality of the group. Okay. And order of an any element means the least positive integer if it has, for which a to the power k is identity, or it is of order 0, or one may say that it is of order infinity. If no such positive integer for which a to the power k is identity exists. Okay. So these cases are different things, but there is a relationship between these two. Okay. So okay. Okay. So as we have defined order, so one may prove that, for example, suppose you consider Z6 plus, okay, then what is the order of 2 class? Can you say? Just do it. Do it now. That what is the order of 2 class in Z6 plus? Hello, hello. What is the order of 2 plus? What is the order of 2 plus? What we have seen in this example, that just check it on your own, that 2 plus 2 plus is 4 plus. Yes. Then add up to 3 times, you have 0 plus. So the order of 2 plus is 3. Okay. So order of 2 plus is 3. What is the order of 4 plus? Just check on your own. Then it is 8 plus, that means it is 2 plus. Then add again, it is 6 plus, so it is 0 plus. So it is also 3. What is the order of 1 plus? It must be 6. What is the order of 5 plus? It must be 6. What is the order of 3 plus? Just look at the example. It is 2, right? 2. Now, looking at the orders of the different elements of Z6 plus, you you will find that for the cases of generators, the order coincides with the order of the group, right? Order of 1 plus is 6, order of 5 plus is 6. Since these are the generators of Z6 plus, so their orders coincide with the order of the group, the number of elements of the group, right? So that's an uh, uh, interesting observation, right? So whenever we are looking at the generators of a finite group, their orders may be equal to order of the group, right? Right. So we are looking for one result, that uh, that this feature might be true in general finite groups, right? Okay. Now, if you look at the group Z plus, then the generator 1, so does it have any finite order? No. This generator, this 1, so the order of 1 is 0, or order of 1 is infinity, right? There exists no positive integer for which this one adding up to this positive integer, suppose k0, it will not give you the additive identity 0, right? So that means this one has order infinity. Or if you look at the -1, then the same thing is happening, right? Not only that, if you take any element of Z plus, any integer, it doesn't have any finite order. Okay, okay, fine, great. So, in connection with the with this theorem, so we can write down one statement out of here that that for the group Z plus Zn plus uh, order of A class equals to n, that is the order of the group, if and only if GCD of A comma n is 1. Now, if one class that generates Zn, so it must be true that the order of that generator must be equal to the order of the group, right? Right? So it must be equal to the order of the group, since that element generates the group, right? So we can write down one note that let G be a finite group, G be a finite group, finite cyclic group, right, of order n, which is generated by, suppose, A, small a. Suppose G is generated by this small a. That means G L angle R angle A, right? And in general, we have seen that this cyclic subgroup looks like that. A to the power n belongs to Z, right? But what it turns out to be, being a finite cyclic group, so it is of great interest to us. We are interested to look at the finite cyclic group, so how they look like. What are the exact distinct elements of this group, right? Right? Okay. So, fine. So, suppose we consider any arbitrary member of this group, okay, member, say a to the power m, okay, take any element of this group, okay, I should write it as a to the power k, yeah, okay. Now, since it is given that G is a group of order n, that is G has only n many elements, okay. So, using this n, what we can do with this element? So, we can apply division algorithm to this power. So, applying division algorithm, there exists QR belongs to Z such that NQ plus R, right? Where R is the remainder in the division of M by N. So, R might be 0 less or equal to R less than N or equal to N minus 1, right? So, if you take any a to the power m, if you consider the power of that element, that is m, and applying division algorithm, you will find that in the division of that integer m with respect to n, it will give you one remainder r, which lies in between 0 and n minus 1, right? So that means, so a to the power m equals to equals to a to the power n cube plus r, right? Okay, so that means it is a to the power n n cube a to the power r. That means it is a to the power n to the power q dot a to the power r, right? Right? Okay. Now, 1 minute. Okay. Yeah. Okay. Fine. So now note that order of G is n, right? Order of G is n. Okay. Then what is your a to the power n? What is your a to the power n? So then we claim that a to the power n must be e, right? A to the power n must be e, right? So yeah. Okay. 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 So now if you we consider the elements a to the power k belongs to z, then being a finite set, so being a finite set, uh, being a finite set, for every k belongs to z, a to the power k must be in G, and this implies that there exist two distinct integers Rs with r greater than s, such that a to the power r equals to a to the power s, and then a to the power r minus s equals to identity, right? This r minus s equals to identity, right? Now if, okay, okay, okay. Now if r minus s, uh, okay, fine. Yeah. Uh, yeah. Okay. 1 minute. Okay. Yeah. Hmm. Okay. So if we let order of A is n naught, say, right? Now since you have you have one positive integer r minus s, for which a to the power r minus s is e, and using well ordering principle, you will have one least positive integer n naught, for which a to the power n naught is identity, right? Say then then uh, then this says that this says that what is that n0? So this says that, yeah, okay, okay, uh, yeah, hmm. So this says that, okay, what I have, okay, so this says that, yes, says that n0 is the least positive, sorry, positive integer for which a to the power n naught is identity. That is e a square a to the power n naught are n naught minus 1 are distinct elements in G, right? And and any element a to the power m belongs to G will be will be a to the power m equals to will be uh, given by using division algorithm division algorithm to the division of m by n naught, that is m can be written as n naught q dash plus r dash, where 0 less or equal to r dash less or equal to n naught minus 1. So will be given by using division algorithm. Yeah, this implies so a to the power m will be a to the power n naught to the power q dash dot a to the power r dash, right? Now what is a to the power n naught? A to the power n naught is identity. So that means it is e to the power q dash dot a to the power r dash. So that means a to the power r dash, where r dash is 0 less or equal to r dash less or equal to n naught minus 1. So any element of G coincides with this a to the power r dash. So hence, so e a square a to the power n naught minus 1 are exactly the elements of G, right? But what is the order of G? It is n, which proves that n naught equals with n. That is, order of A is n. That is order of G, where the distinct elements are e a square a to the power n minus 1. Fine. So if you have a finite cyclic group of order n, which is generated by some element a, then order of A must be equal to the order of the group. Okay. So this proves that if in a finite cyclic group G proves that in a finite cyclic group G, if A belongs to G, be a generator of G, then order of A must be equal to the order of the group. Okay. Okay. Right. Okay. Now one may ask about the converse of this statement. That is, now if we have uh, yeah, so okay, yeah, okay, fine, okay. So if we have uh, a finite cyclic group G, which is generated by small a, then order of G equals to order of A. Okay. 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 So these things coincides. Okay. Fine. Okay. So therefore, now we come to the this statement that the theorem was that in Zn plus a class belongs to Zn has order n if and only GCD of a comma n is 1. Okay. And if it can be proved, then you can say that any A having this property will be a generator. Yeah, and yes, I should write down. And if uh, order of A equals to order of G, then A is a generator of G. Yes. Yeah. That is the okay. Fine. So if you look at the elements of the group and you find that some element satisfies the property that its order equals with the order of the group. Okay. Then you can say that this will be a generator. Okay. Fine. Okay. So what is the proof of this theorem? Suppose A class be of order n. Okay. Then you need to prove that GCD of A comma n is 1. So let GCD of A comma n is D. Okay. Then then what you can say, GCD of A comma n is D. Then uh, okay. And suppose D greater than 1. So you need to prove that D is 1. So suppose D greater than 1. Then what will be the proof of this theorem? Yeah. Can you say something on that? Can you guess? Now, since GCD of A comma n is D, then you can write uh, so D divides A and D divides n. So D divides A and D divides n, right? So A is dr, n is dr dashed, right? Then what you can say? What can you say? Hello. So since GCD of A comma n is D, so there exists xy such that ax plus ny equals to D, right? Right. Then what you can say? Mm. Then n by d a. What is that? N by d a. That means it is n a by d, right? Since a by d is an integer, a by d is r, right? So it is nr, right? Then if you take, so then so what is nr class? Since it is a multiple of n, so it must be 0 class, right? So that means, n by d a class is n by d a class. That means n a by d class and that means it is 0 class. So if you add a class up to n by d times, it gives you the 0 class. So that means, but it has order n, and n is the least positive integer for which na class will be 0 class, right? So you must have n must be less than or equal to n by d, right? Right? So n must be less or equal to n by d. Then what does it prove? So now d greater than 1 implies that. Now since d is greater than 1 and you divide n by d, so that must be less than n. N by d is strictly less than n, right? Which leads to a contradiction. And hence, so d must be 1, that is GCD of a comma n must be 1, right? Fine. Conversely, suppose that GCD of a comma n is 1, and we claim that our claim is that order of a is n, order of a class is n. Okay, GCD of a comma n is 1, so our claim is that order of a class is n. Suppose order of a class is n naught. Okay, now note that n a class, if you add a class n times, then it gives you 0 class. So this implies n naught must be less or equal to n, because n naught is the least positive integer for which order of a class is n naught, right? So n naught must be less or equal to n. Okay, then what follows from here? What you can say? So GCD of a comma n is 1. Then then what you can say? So let, if possible, n0 is strictly less than n, right? You want to prove that n0 equal to n, but you are assuming that n0 is strictly less than n. Okay, then 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 so now GCD of a comma n is 1 implies that there exists xy such that ax plus ny equals to 1, right? Right. So this implies, so yeah. So what does it imply? So now if you multiply this equation with n naught, then it gives you n naught ax, n naught ny equal to n naught, right? So that means, so n naught, you can take this one. So n naught 1 class equal to n naught a plus x plus n naught ny class. Okay. So that means n naught 1 class equals to, what does it give you? So this is 0, this is n naught a class x class plus it is, since it is a multiple of n, this one, so it must be 0 class. So that means, so now it is 0 class plus 0 class, that is 0 class. So it gives you that order of 1 class is, order of 1 class is less or equal to n naught, right? Since n naught 1 class is 0 class, and order of 1 class must be the least positive integer for which order of 1 class is 0. So order of 1 class is less or equal to n naught. But what is order of 1 class? Order of 1 class is always n. But order of 1 class is n. So n is less or equal to n naught. Right? So if you just so this leads to a contradiction, right? As you have assumed that n naught is strictly less than n, so how could it be possible that n is less or equal to n naught? So the only possibility is, so hence this proves that n naught and n are equal, that is order of a plus is n. And this proves that corollary, a class belongs to Zn plus generates Zn plus if and only if GCD of a comma n is 1, right? Right? So GCD of a comma n is 1. Good. Very nice. Okay. And okay. So I would like to write down one more note regarding the discussion that I have already depicted in some previous lines that in general, so let G be a group and A belongs to G, right? Has finite order. Say n. Suppose G be any group, finite, infinite, whatever it may be. But you have an element in G having finite order. Then actually you have, so order of A is n, right? N, but it equals with the order of the cyclic subgroup generated by A, right? That we have proved. So in general, suppose G be a group and A has finite order, say n, then the order of the element coincides with the order of the cyclic subgroup generated by A. That we have proved actually. Okay. So just take this as an exercise and write down the proof again on your own. Prove this on your own. So this is your task. Just okay. So it is your task, and please do it and let me know whatever you have done. Okay. Okay. Fine. So now I would like to finish this discussion just giving you two more characterization of, okay, okay, yeah. So I would like to give you two more necessary and sufficient conditions for a subset H of a group G to be a subgroup. So subgroup criteria, right? So let H be a non-empty subset of a group G. Okay. Then H be a subgroup of G. This is number one. Subgroup of G if and only if for all A comma B belongs to H, AB belongs to H, uh, okay, AB inverse belongs to H, yes. For all A comma B belongs to H, AB inverse belongs to H. Or number two, H be a subgroup of G if and only if for all AB belongs to H, A inverse B belongs to H. Okay. And for a finite group, suppose uh, suppose H be a non-empty finite subset of G of a group G, then H be a subgroup of G if and only For all A comma B belongs to H, AB belongs to. Okay. Okay. So let us have a look at the criteria one, and so I would encourage you to prove the other criteria. Okay. So for one, what you can do is that, so let, so this is one, H be a subgroup of G. Then it is obvious. You do not need to prove anything, right? Because being a subgroup, you always have this condition, this feature. For any AB belongs to H, so B inverse is in H by the criteria that I have already discussed in the last lecture, right? So if you take any element from H, the inverse exists in G. But for a subgroup, that inverse must be included in that set, that subset H. Okay. So for B, B inverse belongs to H, and since A belongs to H, so if you compose these two, A and B inverse, and this composition results an element in H. Okay, so A B inverse belongs to H. So you do not need to worry about that, but you need to prove the converse part. Okay, conversely, let the condition hold holds. Okay, then you need to prove that H will be a subgroup. Okay, okay, okay. Now since H is non-empty, that is a very crucial condition, that H is non-empty. So H, so there exists some H dashed belongs to H. So that capital H must be have some element, since it is non-empty, H dashed, right? Now, uh, yes, then uh, this is your non-empty. Yes, fine. Okay, okay, H dashed. Then what you can do using this H dashed? What you can do? What is your conclusion with this H dashed? Yes. What would be your conclusion? Then H dashed inverse. So that is identity in G. Fine. But is it possible that that identity is in H? Yes. Yeah. Is it possible? That this belongs to H. Why? Why it is in H? Why this element is in H? This identity is in H. Why? Why the identity is in H? That is a question. Now suppose it is true that H dash inverse equals to identity. So yes, then it is in H. Then this proves that for any H belongs to capital H inverse. This exists in G, but H inverse can be written as H inverse identity, right? So this H inverse belongs to, so sorry, you need to write it as EH inverse, right? Right? Okay. So H inverse can be written as EH inverse. So by the condition that if A and B in H, AB inverse belongs to H. So you have assumed that E belongs to H, right? So then E H inverse belongs to H. So this belongs to H, right? Okay. And also for any H comma K belongs to H, then this implies H comma K inverse belongs to H, right? So this implies, so so yes, so H K, so inverse of K inverse, so that belongs to H. So that means HK belongs to H, right? So so this proves that the composition is satisfying the closure property under the subset H. Okay, and now this is true as by the condition, since H dash belongs to H, so H dash inverse must be in H by the condition, right? So that is why we need to consider this condition that AB inverse belongs to H, just to make a guarantee that identity must be in H, and this will help you to prove the other properties, right? So the condition is needed for this one, first of all, and then you are applying this case and applying the condition to the other cases. But that is crucial, that to make a guarantee that that identity of the group will be included in that subgroup, in that subset, and it will be guaranteed by this condition. AB inverse belongs to H, and H must be a non-empty subset, right? So you need to have one element in H. That would suffice. Okay. So H dash in H, so H dash inverse belongs to H, and it is identity, since these are the elements of the group. So you can compose, and this will result the identity element, and this identity belongs to H, and then you can say that every H has an inverse in capital H, and for any two elements HK, their composition is in H. And also, since associativity is an universal property, so once it holds for a bigger group, then it will hold for any subset. So associativity holds, right? Associativity holds easily. So hence H forms a group actually. That is, H is a subgroup. Now, keeping these things in mind, I would encourage you to prove the criteria 2 and criteria 3. In criteria 3, you do not need to impose the existence of inverse in H, because H is a finite subset. So the only thing you would require that for all AB belongs to H, the composition satisfies the closure property. So that is enough. Okay. Okay. So with this one, I would like to end our discussion.